Okay, so we're going to continue with the parallel algorithms part. Just a quick recap of last time. So we had a very quick introduction to parallel algorithms. We went over some complexity analysis. We looked at the work depth model, and we covered prefix sum and parallel select. I'm assuming there are questions. In general, did everybody understand prefix sum and selection? No. You stopped by. Everybody else is fine with it? Did you have an issue with the prefix sum or? Okay. So today we're going to sort of quickly go over search, and then we're going to switch over to parallel sorting. And if you have time, we'll come down to communication costs. We can get there. So the search is sort of a straightforward extension. Most of you probably know how to do this, which is that the problem description is that if you're given a list X which is sorted, we're only considering cases because if it is not sorted, then it's a hard problem to parallelize. Of size n, and you've given an element I, and you want to find the index. So think of variations which is in the lower bound or the upper bound, but in this case we just go for the lower bound out here. So sequentially you would use a binary search. Everybody knows how to do a binary search, right? And it'll take you order log n. Everybody knows why? So again, let's think of the hypothetical situation first. What is the parallelizability of something like this if you want to search? Yes, exactly. So I have it here. So in this case, you can actually do it. Work optimal depth is 1 because you can just throw one thread at each of them, and it's going to happen. Is that clear to everybody? Why this is a search is sort of much easier compared to some of the other things we're going to do. What would you do, again, not factoring in communication costs and overheads of synchronization? How would you do this if you had fewer than that? If you had p processes where p is less than n, then it's basically going to be log n over log p because you're effectively going to recurse using each thread now searching in a peerly thread tree effectively. So that's sort of your log base p log n. So each thread, or you can say that I'm going to break it up into those many segments, and each of them is independently going to search in those areas. Yes, no. So it's not how you would do it. So sorry. So you would do a little bit differently, which is that you take your entire segments. Let's say we have 4, p is 4. So you would basically do 4 tests, which you're testing the whole thing. Then you realize that it's in this range. Then all of your threads will again operate on this region, and then they would go again into a subset. So at each level, you're reducing by that factor. The other way to look at it is that instead of creating a binary tree, at each stage you have the option of, say, going to 4, and then you're going to 4 each. So you're recursing. It's not like the other threads stop. That would be sort of the way you would do it if you were in a distributed sense, and then you had options. Because this is hard if you're given a single Y and you want to get maximum performance out of it. On a large scale system, let's say what Google would do, what you would do is to gather a bunch of searches together and say that I'm going to distribute the number of searches. So you're not optimizing on the depth, you're just optimizing on the total, because the complexity of doing that sequentially would be, say, if you had k searches, you would do k searches in log n, which is, let's say, the size of the array you're searching, and then so you can parallelize out there. This is in order to consider the extreme case of parallelizing. If you want all of your threads or all of your processing units operating on all the data at the same time, doing only a single search, right? So basically, at each stage, you're dividing up your search space into a much smaller division. Rather than dividing into 2 pieces, you're dividing it into P pieces. Okay? Is that clear?
It's clear, but I don't know how you got the expression log n by log p.
That is just coming from log base P log n.
Oh, okay.
Base P n, right? So in terms of it, so you can write it however you want. It's the same. So before we get to sort of doing sorting, I want you to consider a problem which is called ranking. Ranking is that you're given 2 sorted lists A and B, and the rank of a given entry in A is basically the number of elements which are there. So it's basically where exactly in your sorted list another element lists. And now you can think in terms of taking an entire array and ranking it in the other one, which gives you the relative location of every element in B with regards to elements in A. So this is sort of a precursor to say you want to merge 2 lists in an embarrassingly parallel way. Again, you want to think in terms of we go about defining these kind of what might seem like trivial problems in order to be able to do it. Because you should appreciate now from the selection example that if you have 2 arrays that are ranked with each other, you can go in an embarrassingly parallel way and insert them or merge them together. Because it gives you the relative location of each and every entry. Okay, is that clear? So how would you do this? Okay. I don't have a slide for that, so what do you think of is the best strategy to do a ranking in this case? In a distributed sense, what would you do?
Give each element of
Distributed sense, this is actually very complicated.
Yes, it is.
Because
Oh,
you have
if
no,
it's-
you don't know how to partition the data. You don't know where to put the B.
In a distributed sense, if I assume that each processor is taking an element of B and find its own rank, then it would be log n, right? It wouldn't be n, which is smaller than n, right? It will only be log n.
Okay. Think about this. I suddenly realize that I'm going to cover this in maybe 4 or 5 slides. So keep this in your mind on how you would actually do it in a distributed sense. And more importantly, what we want to do is to do this in a work optimal way, right? We want to do it in order n because that's how much work you would do in the sequential sense, right? It's not immediately clear, right? How you would do this in a distributed sense, not requiring, say, n log n work.
Is it even possible?
It is possible.
It is?
It is.
Really?
Yes. Again, you need to, it's not going to be, the constants are going to be higher. You're not going to get a single sweep through this and doing it. But the complexity can be, actually you can do it even in some sense a little bit better in a sort of a,
But there's no assumption.
they're sorted, that's it.
Except that it's sorted.
Yeah. So you can do that. So that's basically what it is. And let's take a look at this. I'll come back to it once we do it. So let's actually switch to parallel sort. I'm going to consider merge sort. And it shows up, that's why I think I skipped the slides, because it shows up when you're merging 2 arrays, right? It's a similar problem as merging 2 arrays. Rank is a sort of an intermediate step as you try to merge them. So let's think in terms of parallel sorting. How are you going to do, so everybody is familiar with sorting in the sequential sense, right? If you had to sort stuff, what are you going to use? What algorithm are you going to use? You shouldn't say merge just because I had it on my slide. Okay. What do you think gets most commonly used? Sort is probably implemented in most of your libraries. Do you know what it is? That is. Huh? it's actually not completely quicksort.
It depends on the size of the n.
Yeah, so it's a I think
Above n it's quicksort, and then like
no
above
no
32.
yeah
it's
yeah so
quicksort.
above anything what will fit in your heap it's quicksort, otherwise it goes for a heap sort because it's fast and it can move things around quickly. But anyway, that's fine. We'll get to quicksort in the parallel domain. What do you think? That is quicksort good for parallelization?
I don't think,
Why?
because quicksort can be predictable, like with how the, based on your pivot selection, you can have, in the property, it can be pretty bad, so.
Let's say you choose your pivot smartly, which is actually your standard implementations do some clever pivot selection as well.
Okay.
So anyway, we'll come to that because we're going to cover all of that. I'm going to start with merge sort just because it's sort of much simpler in terms of it. I would go as far as to say that if you're doing at least a shared memory implementation, so if you're doing a multi-threaded implementation, you would probably go ahead and do something like merge sort. Merge sort is not as good for a distributed environment because you're moving too much data, especially when the amount of parallelism is very high. You're building up a tree and you're exchanging data at every tree level, so you want to avoid that. But from an algorithmic perspective, it's easy because it's a divide and conquer. And this holds true for quicksort as well. You're taking your data, you're dividing it into two, and you're doing it in a recursive fashion, so it's perfect, right? So think of how we would go about using or parallelizing merge sort. You take your array, divide it into two equal halves, sort the first two elements by a recursive call. So you're going all the way down to basically the leaf where you have each individual element, and then you're effectively merging them. So fundamentally, all you've done, the key task is how do you merge two arrays in parallel, right? Is that clear? Now, you can think in terms of what you would do for a shared memory implementation is that you would go down, your binary tree is going to be just the depth is going to be log of p, but each individual segment can be sorted using quicksort or whatever your favorite sequential sort is. And then again, the task is that of the parallel merge, right? So, simple example, some values, we went all the way down to the tree root, and then basically we are merging them, and as we merge, when we reach the root, we end up with a sorted array. So, here's your pseudocode version. Again, if it's small enough, smaller than whatever threshold you want to choose, you use your sequential sort. Otherwise, just take each subsection and do a merge sort by a recursive call and then merge. Is it clear? It should be fairly straightforward. In terms of the complexity, it's going to be n log n. This is your standard sequential merge sort complexity, and most of it doesn't change because I haven't really changed the algorithm as such. Let's look at parallel merge. So this is effectively what we talked about, equivalent to the ranking problem, which is merging of two lists. We're interested in creating C, which is basically the union of the arrays A and I, and we have the ranking problem. And I'm just going to speed up a little bit just so that I can try to finish today's thing. So here we have a trade-off between depth optimal and work optimal algorithms for doing this. Okay. So merging using ranking, right? So this is fairly straightforward. This is the way we talked about. You're basically going to rank A and B and rank B in A. You can do this in a embarrassingly parallel fashion. Now, if you search using P equal to NM, which is basically, I'm going for the extreme case as one thread per data element in A as well as in B, the depth is order 1, but the amount of work you do is order n square. So it's perfect from a depth perspective, but the amount of work I do is order n square. So that's not ideal. And anyway, you're not going to have n square processors for this kind of, for a given amount of data anyway. We talked about doing binary searches. The depth is log n, which is fine. We can live with that. but the work is n log n, right? This is what we talked about. So how do you actually take something like this and parallelize it with optimal work? Anybody wants to take a shot at it? So yeah, it's work optimal if only if the parallel work is the same as the sequential work. So the sequential work for this was order n, right? And that's what we want. We don't want n log n, we want. So you figured out, you understood how we have chosen the splitters, right? These are just evenly spaced apart at log m, right? So this is the log m kth element, this is the 2 kth element, and this is the 3 kth element. For each of these, I need to find out where we are trying to merge these two, right? So I want to figure out where this particular element sits in array A. So just think sequentially for a minute. Take one of these elements and you want to find where exactly does this sit in array A. So that's what I'm interested in finding. Where exactly does this fit in? Because then I can take this piece and I'm saying that this piece only needs to be merged or ranked for that matter in this particular segment, right?
So are these blocks already sorted?
Yes, I mean, they're sorted to start with, right? That was our problem definition. Whether we are ranking or, you can't really rank or merge two arrays. It's very difficult. It's like sorting from scratch if you were to merge two unsorted lists, right? Thinking again in terms of the complexity, if I give you two unsorted arrays and say that I want them merged, what is the definition of a merge? You merge, again, probably needs you to define some order on it, which means that you're sorting them first and then merging. So that is limited by n log n anyway, right? Yeah? So in this case, everything that we are discussing here is only possible if it's sorted. And this, as I told you a few minutes ago, is how you would do merge sort anyway. This is one of the steps of merging where you are sorting while you're merging. Is it clear? Yes?
It's perfectly clear. It's clear.
Okay, no, okay, good. So, can you do better than this?
If we can break A also so that the search space of B will be.
It's not going to gain, you're not going to gain much, right? Because you're already logarithmic on that side. Yeah, so in most practical cases, no. In a very academic sense, you can potentially, you can change it to, you can go a little bit further and more aggressively divide it up into not log m, but you can go for square root of m spaces and then it becomes a log of m. But that's completely academic. Any of you are interested in for purely, it's not.
That's double logarithmic tricks.
Yes. So you can, like I said, there are these kind of tricks, but this is important for you to understand because this ends up being, so, you know, the first level of parallelism that you would most commonly see would be to just say that I'm going to use a recursion and I'm going to use a binary tree of some sort or some tree. This is the second thing where, again, the logarithm comes in and how you divide up your work comes in as well. Keep in mind that this looks like an elegant algorithm because you factor in the complexities and you have the guarantees that go along with it in terms of, you know, doing this in a work optimal fashion. So we have looked at the work and the depth, it's clear. So let's switch gears now that you've seen one part of it and we know that we can do sorting in this. If we consider sequential sorting, what is the complexity? I mean, I've already covered it, so I'm coming late to the party here, but let's see, what is the complexity for sorting? N log n. Can you sort faster than n log n?
Yes.
Okay.
If we know the range of the numbers. we can-
Exactly. But in loosely, what sort of sorting would that be?
Our count sort? You mean the algorithms?
No. So typically, the standard case is the limit that he talks about is for a comparison-based sort. So when you have a comparison-based sort, you're bound by n log n. okay? We're not going to cover non-comparison based sorting. I'm giving it to you for a different reason, because we use similar ideas when we try to parallelize this. So the question, of course, is can you sort faster than n log n? And yes, you can go for order n, where basically, do I have a slide on that? Yeah, so some sort of a bucket sort or a radix sort, you can have these variation. And the idea is that I don't need to do a comparison. If I know that my input is well distributed and uniformly distributed, then I can just take it. So assume that you have, let's say I give every one of you a number, right? From 1 to 50, let's say. And then I need to sort this. It's fine because I can just call you one by one and insert you right into the correct position, depending on the number, because I know that I'm going to see each of them. And there are variations that you can do even to handle duplicates and all. In general, it's going to be, so ignore this. It's not going to work very well if it is dense, if it is not dense, or if it is not uniform. Why? Because the amount of work is always going to be different. So the radix sort of is a version that operates on a bit fashion. So it looks at the bit signatures and does sort of groups them correspondingly with increasing to decreasing bit, the significance of the bit, and then gets it. But this is not going to work. But fundamentally, when you think in terms of bucket sorting, this is sort of the idea that we're going to use when we do parallel sort. And I talked about the most popular versions out there, where what we're going to do is to say that given a bunch of processors, let me think of each process as being a bucket. So once I have estimated what the distribution is, and I know where they need to go, I can take my data and everybody can send them directly to whichever bucket or whichever process it needs to go, and then you do a local sort and you're done. So the idea is a powerful one because you can do it. You just have to do a little bit of extra work to make it generic enough. But we talked about quicksort first, right? So quicksort is actually not that bad. So assume we have 4 processes here. Here's just a cartoon, some distribution between them. And so what we would do as opposed to, you can't see it very clearly, you're going to pick a median. You're not going to pick a random pivot. You want to really pick the median. And the moment we talk about distributed computing as such, a very important aspect is going to be of load balance, which means that you want to make sure that everybody gets the same amount of work. Because if somebody gets too much work and there's the other processes which are not getting enough work, then you're going to get a big imbalance in the amount of work your processors are doing, and you're going to pay a penalty for that. So from a sort perspective, balancing out the work is going to be, from a quicksort perspective, is to pick the median. And we'll probably cover this in class next time, but I want you to think about, because we sort of have all the pieces out here, how do you think you're going to select? If you had to select a median, and I'm going to go to the next method after this, and there's an associated problem. We talked about one selection, there's another selection, which is if you wanted to pick, say, the median, or you wanted to pick k splitters from a given distribution of numbers, how would you do that in parallel in a distributed sense? And think both from a shared memory as well as a distributed memory example of how you would do it, and we'll discuss it in class. But think about it. It's not a very hard problem. We sort of have the basics, but it's an interesting problem nonetheless. Once we have done this, what you're going to do, and this is somewhat a little bit different from how you would normally do it in a traditional quicksort sense, is that you will exchange data. So everybody less than the pivot, everybody greater than the pivot, but you want to sort of partition your process space as well. So you want to make sure that once they're divided, and this is going to depend a little bit on how the network is connected, because you really want to factor that in, that once it's divided, all the smaller numbers which are smaller than your median end up in one part of the network, and they're all close together, and the other ones are on the other side. So let's say we had 8 of them, right? So first split is going to be right in the middle. Okay? Oops, it's not. Okay, that's not good. Let's see. Okay. Right? So let's say those are 4 processors with data, and this is the first split. So you're going to have, let me write out the recording mode. So that's why this weirdness is happening. So consider now the same situation. What we want to do here is to do the opposite. We want to do extra work up front, but we want to communicate only once so that I know exactly. So this is like the idea I talked about earlier about bucket sorting, which is like I want to take and say that this data that I have needs to end up with you. So I need to figure out exactly whom to send it, and then it's trivial after that because everybody can sort independently, right? So that's why it's called sample sort. It samples the data and tries to estimate the distribution, and by estimating the distribution, it tries to figure out which process should have which chunk of the data, and then there is a single round of communication where you're sending data exactly to who needs it. Okay. So it's not very clear, I apologize, but basically what you do, and there are variations on this, each process, depending on what data it has, generates a bunch of samples from it. Now for theoretical reasons, and we'll come to it, again, this is the same kind of analysis that you need to know. You can think from the way I've described it, you can arbitrarily choose some number of samples, right? But there are bounds that you can give by choosing the right number of samples. And in this case, we choose P number of samples, okay? So each process chooses P samples. I'm going to define the stereotypical one, and I'll quickly discuss some variations on this. All of these P samples now are sort of gathered together on one particular process. So this is a sequential bottleneck, okay? I'm just describing this is because this is how the algorithm was first described. This process now has how many elements? P squared.
Yeah,
P from each, right? So he takes those, he sorts them sequentially, okay? Now already you should see that this algorithm is making a very important assumption that P squared is still very small. So this doesn't hold up to that, but there are ways around it. So you sort P square samples sequentially.
So from random set, I'm picking up P, right?
Yes.
So if the P turns out, if these P elements turn out to be the same in every.
Yes. So no. So here's the thing. So this is the first version.
Okay.
The simplest fix for this, and which again in practice, I can tell you I've used this a lot of times, works very well, is that you actually add an extra step in the beginning before you pick these splitters. You sort each of these locally.
Oh, okay.
So that the reason I'm presenting this is that is one strategy for choosing the right samples. Now, if you have a different way of choosing the samples, which is intelligent enough or somehow is tailored for your problem, yes, it will work. What you need to try to do is that there are 2 aspects here, right? Are you generating samples, the P samples that you're picking, are they good enough, right? Actually, I have my own variant of this where I don't even necessarily choose from every single process. And some processors maybe may generate less than P samples. This is going to depend on, you can look at the bounds that you want and the level of tolerance that you want. So you can work out statistically what is the number of samples that you need to generate. Now, assuming that your data is well distributed, right, and there is a tolerance that you have, you can choose that. What difference does it make if it's well distributed? So this is the original logic. So by sorting it and choosing samples, we are kind of cheating in some sense. We're just trying to cheat and say that it's going to do better in the worst case. But if you think realistically, if there are large enough number and they're well distributed, if there are no pathological cases, then just randomly choosing P square, which means, how will you choose randomly P square? You're choosing P from each. That's right. That's a good enough uniform sampling of your data, and that should work in the stricter sense. You can go about and design heuristics around it, which is going to address that. Okay. So once you do this, you have this. Are there any problems with this algorithm? The communication is not huge. It's actually optimal from a communication perspective. Where it is a problem, you're right, it's the communication which is the problem. It's not that it's huge in the stricter sense. It can potentially choke your network because everybody is exchanging. So the number of messages that are being sent here, how many messages are being sent? It's p squared, it's order p squared, because each process is sending p messages, right? So that in itself, depending on the size of p, can be a problem, right? So you can look at it. One of my papers deals with this particular issue of how to avoid these problems. But anyway, so here's just the quick look at it. So you randomly partition it into n over p points. So this is dividing across each. You sort locally. So this version I do mention it because in practice it works reasonably well. And then you choose p splitters per processor evenly because it's sorted. It's a good sampling of your distribution. That guarantees no more than 2 n over p elements per bucket. So you can guarantee it, and we can look at the proof if you want. It's not great because you still have a factor of 2 almost. That could be wrong, but it's not that bad. In practice, especially as long as n is sufficiently large and you don't have very weird distributions, you can actually get a much, much better thing. So you gather splitters in P0. As I mentioned, this is a problem, right? You are still having a bottleneck here. What would be a better way to do this? So we'll cover another sorting algorithm in next class, but fundamentally you use another sort algorithm, maybe quicksort in this case. Basically algorithms which are much better for a smaller number of values. So you're going to sort these p squared in parallel using p processors. So right now we're still thinking of n being much larger than p, but what if it's much more comparable? So you can do that. So you sort these splitters and create buckets, exchange data, and then once everybody has their respective data points, you can just sort them locally and you're done. Is there a situation where this will fail? The algorithm. Fail can be both from a correctness as well as the system not being able to handle it. Or can you see a situation? Try to think of it. Those of you who are thinking in terms of large-scale data analytics should really think about this. What is the distribution for a lot of the web data, your social networking data? Yes, so what will happen with the power law distribution? What can happen potentially?
Well, the question is how would you choose the splitters?
Yes.
So if it happens that we have many numbers that are very close to each other, that are almost the same, then one partition or one splitter will receive most of the numbers. Let's say if it powers.
Yes. So with power law, what can happen, because you have a small set of numbers which are dominating so huge, we are dividing it up into n over p segments. It's possible that in the ideal situation, forget how the algorithm does, that say the number 2 in this case has more than n over p entries. There are so many duplicates that your splitters are no longer good enough. You need to split more than just figuring out the value. So if you have that many duplicates. So this is something you should again think of when you are looking at algorithms. What appears to work might fail in situations where your data is so weird. This is also somewhat, so there is a very easy way to fix it. Any ideas? How would you fix this? How do you change this algorithm to handle, extreme number of duplicates? Most of your array is the same. How will you sort it? If you've ever thought about convention in your sequential sense, do you know what a stable sort is? What is a stable sort?
Keep sorting over iterations. The order of sort
It doesn't, so if for them the data being the same, it doesn't move them around unless it's, so if you had the same data and you sorted it. So not all our algorithms will guarantee that, right? So the fix for this is somewhat related to doing the same thing. Because the way you will fix it is that you keep not only a track of the value itself, you change the comparison to respect the original index, right? So the moment you factor that into your splitters, you can actually span, because you've effectively increased the dimensionality of your comparison function. So you added an extra dimension based on the original ordering of the numbers of the duplicates, so to say. So then you can actually fix it. But these are issues you should think about in terms of what happens when numbers become so large. You really have to think about sorting arrays where you would have duplicates in such a large quantity that they won't fit on a single process, right? So these are somewhat pathological, but you'll be surprised when you actually start dealing with these that they do arise and can happen. Here's just a very quick rundown of the complexity of each of those steps. And the first sort locally should be fairly clear. This is just a call to the local sort. So again, the first and the last steps. Selecting the P1, P-1 splitters per process is order P. Is that clear? That's easy. Gathering the splitters on a single process, if you decide to do that, is order P squared. Is that clear why? You're gathering P, he's still gathering, the single process is still gathering P squared. So there is a sorting that is going to be P squared log P. Broadcasting these. We haven't covered this yet. I'll go through this. The log P terms comes from a communication model. It's basically because even though you're sending from one to everybody, you do that in a tree-like fashion, similar to what we were doing for the prefix sum. You don't want to send one guy sending to everybody. You'll send it to in batches, right? So the cost of a broadcast is log P, and we are broadcasting P splitters. So the cost of doing that is P log P, and finally a sort again, okay? Here is the thing. I'll go through this very quickly. I want, because we are out of time, I want you to, it's the full proof. I want you to go through this, convince yourself that this works. I'm going to put up the slides online. If not, we'll ask. It's actually a very simple thing, and this is how you would go about analyzing this. And the general idea is very simple, that all entries on basically a particular process are basically greater than a given splitter and less than or equal to the next splitter. That's how we define it. So you try to count the number of elements of the sample which are less than the ith splitter, which is this. And so that's basically the number of splitters which are less than that, and correspondingly the number of the lower bound on the number of elements, because each of the splitters corresponds to n over p square elements which are guaranteed less than that. Similarly, you try to get an upper bound on the number of elements which can be greater than the given splitter. And so then the logic is that by combining these two, the maximum number of elements on any given processor is going to be the total number of elements minus the upper bound minus the lower bound on that. So basically you're getting rid of either side, and that's the maximum, that you have the worst case scenario on one end for the lower bound and the worst case on the upper bound, and that gives you the number which basically the expression is 2n over p minus n square over p, which is definitely less than or equal to 2n over p. That gives us the bound. Look through this, convince yourself that it is clear, because you will, as you start looking at partitioning data, you will have to generate these kind of bounds and analyze it and make sure that you